Welcome back. Of course, we can't talk about all these transformations without touching on a dipole term, of course, and the, vector potential thereof. So the statement reads, an ideal magnetic dipole M is located at the origin of inertial system S bar that moves with speed v in the x direction with respect to system S. In S bar, the vector potential is A bar equal mu naught over 4 pi m bar cross r bar, r hat bar, over little r bar squared. And the scalar potential V bar is 0. Okay. A. Find the scalar potential V in S. B. In the non-relativistic limit, show that the scalar potential in S of that ideal electric dipole of magnitude P equal V cross M over C squared located at O bar, or the origin in the bar system. Okay, got a lot to deal with. Let's take it one step at a time. All right, so to start, let's go back to what we first defined as the potential for vector. Here we see that we have the scalar potential over C. Again, in all the other four vectors, this had to do with the temporal. Here it's the scalar, and here we have the vector potential being constructed into the three dimensions that we know as the spatial. Okay, we like that. It's actually a very, very clever construction. But what we see here is that V is equal to gamma V bar plus V AX bar, because again, we're told we're moving in the x direction. So if we plug everything in, again, V bar was equal to 0 in that transform frame. And notice that V plus the everything we had in a bar system. We transform that R hat into the R vector, which means that we have a cube in the denominator now. Again, R hat is equal to vector R over R. So plug that in, combine down there. Again, only interested in the x component. So here, what we see is that M bar cross Z bar, or excuse me, M bar cross R bar for the x component is equal to this, and we can go ahead and tell you that if that's the case, we have my Z bar minus mz y bar, but again, based on the fact that we're moving in the x direction, Z and Y bar are equal to the Z and Y coordinates. We like that. So what we can say here is that we have V equal gamma times the velocity mu naught over 4 pi my z minus mzy over r bar cubed. Okay. Now for the position here, we have x bar is equal to gamma x minus vt. We'll just call that gamma rx. Similarly, we have y equal y bar, which is equal to ry, and so on and so forth. Here, capital R boldface is the vector in S from the instantaneous location of the dipole to the point of observation. Okay, so we had script R to begin. Now we're using capital R for that reason. So x direction, y direction, z direction. Again, we're only moving in the x direction, so gamma only gets tacked on to Rx. And let's continue this process. We see that for little r bar squared, we just have gamma squared on Rx and square the y and z terms. Here, what we're trying to do is use this concept of putting everything to a gamma. And in order to do that, we know that we can add 0 to anything and get the thing back. So that's the additive identity. And we're writing 0 in this case with gamma squared r squared minus gamma squared r squared. Similarly for z, add a quantity minus the same quantity, so we're algebraically equivalent. But as far as little r bar squared, this is all we needed here. But here we're doing this, so we put a gamma into everything and write big R. As you see here, what we did was factor out the r bar squared with all the positives. And then we did a 1 minus gamma squared, so we could still write this as positive. And that was just a clever manipulation of sorts. Algebra, of course, being our friend is what we wanted. So, moving forward then, if that were the case, we have, and if theta is the angle between r and the x-axis, so we can start writing things as dot products or cross products, then we see that we have ry plus rz is equal to r squared sine squared theta. Okay, so that being said, now we have more algebra work to do. So little r bar squared we see was gamma squared r squared from this, and then we see we have gamma squared times 1 over gamma squared minus 1. And let's rewind and see how we got there. If we factor out a gamma squared here, that's pulling out here, so we have to force factor and divide by a gamma squared in the 1 part. So that's how we get this parenthesis here. This came from the fact that we look like a dot product, or a cross product rather, at that spot. No, this would be dot product, re-referencing angle otherwise. So with that being said, be careful of that. Again, three-dimensional dot products can get messy and you will have a sign on there. But we see here that the 1 over gamma squared is equal to the 1 minus v squared over c squared due to the Lorentz factor. So the two 1's cancel, and that's how we're left with v squared c squared here in this parentheses. And after that, that was just a bunch of simplifying to consolidate. You see we have gamma squared r squared in this term, a gamma squared and r squared in this term. Pull them out. And then we're left with 1 minus v squared over c squared sine squared theta. Pretty good there. And then, if that's the case, plug that into the denominator. We see what we get here as far as a cube. Of course, we had to take the square root of this r squared term. Hence why we just get a gamma r and a square root there. And that's what's cubed. But you see, we kind of saw this earlier when we dealt with moving point charges needing that sine squared term. This is the idea of where it comes from. Anyways, to simplify this down, then we just cube everything here. You see that 1/2 gets to a 3/2 power. Gamma cubed, r cubed, cancel away. And then if that's the case, we see that v dot m cross r is equal to v, which is already in the x direction, times m cross r in the x hat. So that being said, we have this, and what that allows us to do is back sub in the dot product here, and then we could plug in, if we wanted to, what this gamma squared is, which is 1 minus v squared over c squared. It's not always easy, it's not always clean, but this is the potential and S from S bar. And then if we want, we know what mu is because we can relate mu and the speed of light to epsilon, and so we do that here. And we also know that from the vector product identities that we see in the cover, that we can rewrite this in terms of r dot v cross m, and that makes everything tidy up quite nicely. So be careful. We get our c squared for relativistic, r squared, capital R, so we're following the same guidelines that we need for these things. V cross m is what we're trying to show. We have the gamma factor there, and in here we see that sign depends on which direction we're moving with respect to the axis, so we're good pretty much everywhere. Now all that's left to show is what happens in the relativistic limit, i.e. v squared is much less than c squared. If that's the case, then we see that the v over c term goes to 0 on both of these things, and we're left with a 1 times the numerator and a 1 times the denominator, because 1 to the 3/2 is still 1. That being said, if we're looking at the relativistic dipole as v cross m over c squared from the transformation rules, we see that we have 1 over 4 pi epsilon naught, easy enough, r and r squared still there, and we see that color coordinated in the purple is what we're writing as the dipole term there for the electric dipole, which is the potential of the electric dipole as we just discussed. So it's really, really cool how quickly these things can materialize in one frame to another. Magnetic and electric being tied together like that is really fascinating to me. But this is why we have to have tools like the relativistic regime in order to exploit the things that we know about our physical intuitions. That being said, we got a lot more to cover with this stuff, and it's really, really fascinating. So can't wait to see you all next time.